announcement at 3 o'clock, so after Ulti's talk, we'll have a conference photo by Peter, and Ani has a drone, so they're also going to be video.
Video?
Huh?
Video.
A video, yes. So, be there in here, and we'll go out there.
Okay, so our next speaker is Nat Tantivasadakarn, who's going to tell us about non-invertible duality symmetries from ZX calculus. Thank you.
So thank you very much for the invitation. It's my first time in Oxford, so I'm very excited to be here. Today I'm going to talk about non-invertible duality symmetries from ZX calculus. And so before I begin, I'd like to thank my collaborators, which are Pranay Garanthala and Shuheng Xiao. And so this is sort of a combination between me, a sort of condensed matter physicist, working with these two guys, which are high-energy physicists. And an interesting thing about these two authors, as actually commented by Nadi, is that one of them is a former student, one of them is a former postdoc, and one of them is his imaginary part. So let me just begin the talk. What I want to talk about today is duality transformations. And what is a duality transformation? Roughly, I think of it as we're trying to view a system from a different angle, such that it can offer insight into its properties. For example, me as a condensed matter physicist, we may have some description B, which might be a little hard to explain, but maybe we can do some sort of transformation to turn it into something simpler that we can understand. And moreover, this duality transformation, we might be able to do it for a family of Hamiltonians. So we might be able to tune some parameter and maybe even rotate one into the other. So you can even tune this family, and maybe at the end of the day, you sort of what one picture was into the next. So a famous example where this happens is the so-called Kramers-Wanya duality, which Paul talked about this morning. And that happens in the transverse field Ising model. So the Hamiltonian consists of an Ising term made out of two z's and a transverse field made of x. And we know the phase diagram of this 1D model pretty well. When there's no transverse field, we just have a ferromagnet where the Z2 symmetry is spontaneously broken. And when H goes to infinity, we have a paramagnet, and there's a transition somewhere in the middle. The Kramers-Wanya duality roughly tells us that if we roughly swap ZZ with X, we get the same Hamiltonian back up to some rescaling where the transverse field has now changed from H to 1 over H. And so in the spirit of the picture I showed you earlier, one nice thing is that we started with a ferromagnet. If we look through the mirror, it becomes a paramagnet. You can tune through the phase transition, right? And the interesting thing is that once you go through the other side, they swap. What was the ferromagnet became the paramagnet, what the paramagnet, But the interesting thing is that at the midpoint, the critical point, these two pictures look the same. So this Kramers-Wanya duality, you can think of it as acting as a symmetry at this critical point. Okay. So this Kramers-Wanya as duality symmetry is interesting because it's a non-invertible symmetry. So what are the symmetries of this Hamiltonian exactly at this critical point? Well, there's the usual spin flip symmetry, which is Z2 symmetry, where you flip all the spins using product of X as an order 2 operator. You also have translations, which shift everything to the right, for example. But the Kramers-Wanya duality, what it does, it sends X to ZZ and ZZ to X. But the interesting that happens in the lattice is that, well, there's some funny mixture with translation. And this, the continuum was known for a while. It's sort of just the Ising fusion category. But on the lattice, there's this curious mixture with translation symmetry that has just been pointed out in recent literature. And so the question is, how do we try, is there a way to understand where this mixture with translation come from? Can we, why does this appear on the lattice, and does it depend on the sort of choice of lattice model? So this conference, as Sakura pointed out, is a great mixture of different audience from different fields, mathematics, high energy, condensed matter. What I hope to sell today is that I'm going to be trying to use tools from quantum information as a fourth field to try to address topics in generalized symmetries and trying to use quantum information to gain new insights. So the tool that I'm going to be using today is so-called ZX calculus, and let me tell you a few fun facts about it. So ZX calculus is sort of like a Lego building block where you take a bunch of tensor and you sort of string them together in order to build interesting maps between qubits. And so you can start with these simple building blocks, glue them together, and try to build an interesting operation out of it. And these tools give you a way to deform these tensors in a systematic manner and allow you to make progress in simplifying them. So it originally started in quantum computations and quantum information, and people have been using it, for example, when they want to do fault-tolerant quantum computation or to compile quantum circuits to use in quantum processors. And another fun fact that makes it very relevant to this conference is that it was also invented here at Oxford. And so you can even read a whole book about ZX calculus if you want to. Okay, so let me give you the outline of what I want to talk about today. I'm going to try to give a very quick crash course on what ZX calculus is. I'm going to then use these diagrams to show you how we can realize this Cramer's 1 duality from ZX calculus. And then I'm going to show how we can generalize these weather settings. One is that in the 3+1D Z2 gauge theory, there is a similar thing to Cramer's 1 duality called the Wegener duality. And I'm going to show how you can also write down an operator for this duality using ZX calculus, and you can actually compute the fusion rules very efficiently in this way. And then I'll conclude, if I have time, with some more general discussion about more generalizing models with such a symmetry and when it does not mix with spatial symmetries. Okay. So let's get right into it. Let me give a crash course in ZX calculus. So the building blocks for ZX calculus are these so-called tensors. There's the green guy and the red guy. Let me focus on the green guy first. The green guy, you can think of it as each leg being a physical qubit, and the states that are non-zero are exactly a GHZ state. It's a ferromagnet. So the only coefficients that are non-zero in this green tensor are either all 0 and all 1. It doesn't matter how many legs it has. Here I'd drawn 3, but you can have more if you like. So if you're confusing green and red, just remember the green stands for GHZ, so it's a ferromagnet. People in ZX calculus call it the green spider. You can also think of it as being a copy tensor, because if you write it in terms of component, it's sort of just a delta function. So whatever I is here, j and k have to be the same. Okay. And these green tensors satisfy certain properties. For example, we know that this is a tensor, a state which is a ferromagnet, so it has a +1 eigenstate if I act with poly z's on any of the 2 legs. And moreover, we know that this ferromagnet has a Z2 symmetry, so we can flip all the spins on all the legs. So if I apply X on all the legs, that is also a symmetry of this tensor. The red tensor, or the red spider, is just a Hadamarded version, or in some sense a Z2 Fourier transform of this tensor. I just change 0 to plus and 1 to minus. And if you expand out the components, it turns out that these tensors are just saying it's sum. It turns out that it's just saying that I plus j plus k has to be 0. So you can think of it as a sum tensor if you want. And people in ZX calculus call it a red spider. And so the relations, since I just did a Fourier transform or Hadamard, is just swap from the green tensor. You can either act with 2 x's on any legs and z on all legs, and it does nothing to that tensor. That's the symmetry of the tensor. Okay. Now, more generally, you could have more general tensors where I put a phase e to the I alpha in front of it. Yes?
Can you go back one slide?
Yes.
So, I've not understood the framework. I mean, do you have qubits attached to the edge? The edges?
Right. Each edge, you can think of it as a qubit if you want. So there are 3 of them here, and the state is just all 0 plus all 1.
I'm not understanding what is the difference between 0, 1 and plus or minus 1.
Plus is just the superposition of 0 and 1, 0 plus 1. And minus is 0 minus 1. Sorry, this is just a QI lingo, but yeah.
Okay.
It's an X eigenstate, yeah, if that helps. Yeah, this is Z eigenstate and this is X eigenstate. Yeah.
So you will write for the the state on the right and the superposition of states on the left.
Yes. Okay, any other questions? So in general, I could have a phase e to the I alpha in front of this GHZ. I won't really be using that today, but that's what ZX calculus people do. Another important thing is the Hadamard operator, which I'll represent with the yellow box today. It's going to just swap X and Z whenever you find them, and it'll also swap green and red. And so some interesting, you can realize different states already with ZX calculus, for example. You can initialize or project to a state with a single green tensor. You can write down Bell pairs, you can write down GHZ states, and you can even write Pauli operators in this way.
Nat?
Yes.
Are you reading from left to right?
Yes, I'll try not to make that a problem too much, but for now it's left to right. It's a bit unfortunate because QI people like to write left to right, but the equations go right to left. So, okay. A nice property of these tensors comes under the slogan that only topology matters. So it doesn't matter whether I wrote it like this or like this or like this. It's all sort of the same. So you don't need to worry about it. You can flip it. As long as you keep the input and output legs fixed, whatever you do in the middle doesn't really matter. Okay. And now what's powerful about ZX calculus is there are a bunch of so-called rewrite rules, which I'm not going to go through all of them. I just want to give you a feel of what it's like. But for example, the first one on the top tells you that if I have a ferromagnet and a second ferromagnet, I fuse them together, I get a bigger ferromagnet, right? Sort of intuitive. If you take two Fourier transforms and you multiply them together, they cancel. For those of you who are familiar with Hopf algebras, let me comment that ZX calculus is basically sort of like a souped up version of Hopf algebra. So the Hopf algebra is for Z2, and there are familiar rules you might already know, for example, this bi-algebra, Hopf rule, right? So the red tensor, which is sum, is just multiplication in Z2. Addition, right? And the green tensor is just co-multiplication. And these fusion rules are just associativity, co-associativity, and then there are other rules that come from the Hopf algebra. It's just that you can have these phases, and you don't really have to restrict yourself to multiplying once. You can multiply many times, co-multiply many times, and that's why you can have many legs coming out of your tensor. Okay, so that's all I'm going to say about ZX calculus for now that we'll need to use. And now I'm going to talk about how we are going to represent our Kramers-Zwanny duality using these operators. So let me take a little detour, and I just want to talk about how we gauge a Z2 symmetry in the lattice. Let me tell you the answer, which is more or less implementing this the Kramers-Zwanny duality. In the Ising model, I said that the Kramers-Zwanny duality sends X from one operator to ZZ on the other side. So let me convince you that this operator does the job. So if I start with X down here, and I use this operator, I have this green tensor here as a GHZ state. And remember that the symmetry of the GHZ state is I can spin flip every spin, right? So an X over here, since it's a Z2 operator, I can push it into X on this side and X on this side. Next, I can push it through the Hadamard, X becomes Z, and then I use this rule here to say Z over here is equal to Z on the other leg. So I can do the same thing for the left leg and the right leg. So I've convinced you that X down here can be pushed all the way through to Z, to two Z's on the other side. So that's how I map the transverse field term to the Ising term in the transverse field Ising model. So this operator does the job. And so you can actually think of this process as gauging a symmetry if you do some small deformations. I just use this fusion to sort of split out a green dot here and a green dot under here. And you can actually think of this process as gauging. So if I start with my input state as some sort of matter field, right, what I'm doing here in the first step down here, let's have time flow up. I can initialize extra degrees of freedom, which you can think of it as gauge fields in some particular state, say the plus state. I'll then apply some unitary, which is actually related to a Z2 times Z2 SPT, which you use for the gauging. And then I do some projection. I apply this, I project to some certain state, and you can think of this as projecting to the gauging subspace, and that's performing this sum over here. So you can actually show that this whole process is basically gauging a Z2 symmetry, and then you're going to get a dual Z2 symmetry, and this is what this map is doing. So Kramers-Wanier, you can think of it as gauging, but it's taking you from your matter degree of freedom to your gauge degree of freedom. So you're changing the Hilbert space. If you want to make this exact, like Paul mentioned this morning, you sort of have to cheat a bit, and you have to sort of move all your sort of gauge qubits back to your matter qubits. So you have to cheat a bit and turn everything back, doing this half translation. So if you incorporate this half translation, then this becomes an actual map only on your original Hilbert space. So you can think of it as there's some map here which takes you from sites to links, right? And then there's a half translation which takes you back from links to sites. And so the nice thing of writing the operator this way is that it's inherently translation invariant. And that's the form of the Kramers-Wanier operator. Now we can try to compute. Of course, people have computed this before. I just wanted to show you how this works with ZX. So suppose I want to compute D square. There are a bunch of steps I won't walk through. I just want to give you a feel of how it works. You're going to compose these 2 times, and you're going to note that if I can move this translation through so that I get this computation where I have a full translation, and then I just need to compose this gauging where I go from sites to links, and then gauging links back to sites. So the gauging links back to sites, I have to do this computation. You have to simplify this. But for example, I can use Hadamard to turn the green guys into the red guys. I fuse the red guys together, apply the bialgebra rule, and fuse all the green guys together. So there are a bunch of steps you can do, which you can use to simplify your tensor. But at the end of the day, you can prove rigorously that you get some sort of operator which looks like this. And this operator turns out to be up to a constant projection into the symmetric space of your Ising model. So you can prove rigorously using ZX calculus that D square is up to a translation over here, 1 plus eta. So that's sort of the Ising fusion rule we're familiar with. Okay. So this is how we do it. And now we want to go to higher dimensions. And of course, higher dimensions, there are people studying tensor networks in higher dimensions, but they're often very hard to simplify unless you have a specific structure to allow you to simplify these tensors. And so it turns out that ZX is a great tool for that. And so what I want to study next is the Wegner duality in 3+1. So the setup for the Wegner duality is that now I have a cubic lattice. I place my qubits on the edges, and for each vertex, there is a Gauss law I impose. So it's not a tensor product Hilbert space anymore. And there are 2 terms similar to the Ising model. There's a transverse field as usual, but now you have a plaquette term. And now there are 2 phases. If there's no transverse field, I have a spontaneous symmetry breaking of a one-form symmetry, which is defined as a product of x's around any membrane. This symmetry is spontaneously broken, and I'm in the deconfined phase, or the toric code phase. And then when h goes to infinity, I go to the confined phase, or the trivial phase, and in the middle, unlike the 1D where you have a second-order transition, you have a first-order transition. And so this transition point is self-dual under gauging this symmetry. So there is some symmetry that over here. And in the continuum, this has been studied before, but now we want to see what happens. And in the Euclidean lattice, let's see now what happens at the level of the Hamiltonian. So what does this Wegner duality do? Well, it's roughly sending this x term to the plaquette term. So the operator D will send x to this ZZ, and this ZZ back to x. And so what it does to a loop here is that it sends it to a bunch of x's, and this is sort of the picture that people have realized into the continuum, is sort of sending the order operator to the disorder operator on the right. Okay, so we can do some similar trick. We define first an auxiliary Hilbert space. You can think of it as where the gauge fields live. You go from the links to the plaquettes, and then you go back to the plaquettes and links, and if you compose them together, this gives you the action of D square up to some translation in some direction. And so we did that computation, and we found that, well, after you try to simplify this, you'd indeed get that there is the result of D squared is just something called a condensation operator. You sum over all the Z symmetries of your model, and you perform some projection. That's you get up to some translation, which we find in this model. Okay, so dx can be used to simplify, and you can show that you get this exactly. Okay. So let's see how I'm doing on time. Okay, I have a bit time left. So I'm going to now comment about when does this generalized Ising model mixes or does not mix with the spatial symmetry. And to mention this, we found a very nice way to formulate everything in terms of graph theory. So for example, I can think of my Ising terms in my Hamiltonian. I can formulate it as a bipartite graph. So for example, think of the Ising model. Let me put all my sides or qubits as black dots and all my Ising terms as white dots. And the rule is I connect an edge whenever my Ising term contains that site. So for the Ising Hamiltonian, right, each Ising term contains two z's, so I have one edge going up, one edge going down, right? And so I get a bipartite graph of the black edges and the white edges, the black dots and the white dots. You can do this for other models if you want, for example, Ashkin-Teller, or you can do it for the plaquette Ising model, where I have, for each plaquette, which is a white dot, I have 4 black dots surrounding it, and I connect an edge whenever this is in my Ising term. So if you have this, and you can have a duality if the number of black dots is equal to the number of white dots. So it means that you can turn each x term into an Ising term, right? So you can swap the black dots and the white dots. It turns out that the symmetries of this Hamiltonian, so an Ising Hamiltonian with a transverse field, can be read out directly from properties of this graph. So for example, the invertible Z2 symmetry, if I write down a sort of biadjacency matrix, meaning I just put a 1, I take the black dots as rows and the white dots as columns, and I put a 1 whenever there's an edge, I get this matrix, then it turns out that the symmetries are actually just the kernel of this matrix. For example, you look at this matrix, it has Ising terms, right? And the kernel is just having 1s everywhere, mod 2. And so that's the symmetry of the Ising model, right? You flip all the spins at every position. For a more general matrix, you just need to compute the kernel of this map, and that gives you all this Z2 symmetries. Now, the non-invertible symmetry also has a very nice interpretation in terms of this graph. I can construct an operator going left to right directly using this ZX tensor. So I take whatever graph I have here, I put it here between connecting the green dots and the red dots, and then I just compose it with Hadamard. So for example, if I use this for the Ising model, I'll sort of get this graph where I push the Hadamard back to the virtual to the virtual legs of my tensor. So we were able to find a nice way of mixing with spatial symmetries. I mentioned that the internal Z2 symmetries are just the kernel of this matrix. It turns out that there are 2 types of symmetries and of this graph. One gives rise to a spatial symmetry, and one gives rise to a duality symmetry. The first is if you have a symmetry of your graph which sends black to black and white to white, that's a spatial symmetry because you're sending Ising terms to Ising terms and qubits to qubits, right? And so this is called a preserving automorphism graph, and that gives rise to a spatial symmetry. On the other hand, the duality symmetry, you can define it whenever you're swapping the black and the white. So for example, in this one, the duality just corresponds to this half translation in this graph, whereas the spatial symmetry corresponds to a full translation. Now, an interesting property is that this duality, which corresponds to a reversing automorphism, swapping black with white, if you do it twice, right, black now goes back to black and white goes back to white, so you get a preserving automorphism. So composing 2 duality transformations always gives you a spatial transformation, and it's whether this thing, and the fusion rule, we can write that out explicitly at this. So it just depends on whether the composition of this map gives rise to a non-trivial spatial symmetry or not. And in the half translation, of course, if you half translate twice, you get a full translation. That's why we found that in the Ising there was a translation. But there's also another symmetry. If I just swap black and white by reflecting, right, this gives an example of a non-invertible parity or reflection symmetry, which squares to a sum, and this one does not mix with translation. So it depends on which symmetry you want. Let me conclude now and just say that what I did today was using ZX calculus as a convenient tool to represent non-invertible symmetries. There are interesting generalizations we might be able to do in the future for qubits, which might give a lattice version of Tambara-Yamagami, right? And let me also mention some related work we did, which show how these tensor also appears for symmetries based on more general Hopf algebras. For example, we found some generalization to non-abelian groups where these X spiders correspond to G symmetries, and these Z spiders correspond to rep G symmetries. So it might be interesting to see what kinds of non-invertible symmetries we can also write with these tensors. Okay, so let me stop here.
Questions?
Easy one, no?
So can you compute other data? So like Tambara-Yamagami things that you're doing? Can you compute also like the Frobenius-Schur indicator with this formalism in some way, or it's very hard?
Yeah, I think it might be possible. I don't know a direct way to do it, but I think what people have been doing in the literature is actually just gauging a subgroup and seeing what symmetry you get as a dual. I think that's sort of an easier computation.
Yeah, but
my experience. Yeah. It's a good question.
That's important if you want to discuss like anomalies and so on.
Yes, I agree. Yeah.
So in 1 plus 1D, if you relax the condition that you want to have a tensor product Hilbert space, then you can avoid the duality mixing with translation.
Yes.
Here in 3 plus 1D, you are already starting with an Hilbert space which is not tensor product. Why do you still get, I mean, is there another formulation in which maybe you can avoid mixing with lattice translation?
So okay, I did that to just simplify the presentation. In fact, you can impose the Gauss law energetically, and there it's the tensor product Hilbert space. It's just the nature of the one-form symmetry. Instead of being a topological, it sort of can called non-topological.
I understand this, but I just want to understand whether you can reformulate in some other, say, model without a tensor product Hilbert space, but avoiding the duality mixing with lattice translation also in 3 plus 1 dimensions.
Yes, for example, you can do the reflection here. You can do like I did in 1D. If you do a non-invertible reflection, it'll also not mix.
Okay, thanks.
Thank you. Any other questions?
On the last slide, you said the phaseless. And Z spiders define G and rep G. So when you include the phase, what do you get?
Yes, I don't know how to include the phase in a nice way yet. So yeah.
The phase is the alpha? Or?
Right. So right now, it sort of more or less looks like multiplication and co-multiplication of the Hopf algebra at the moment, yeah.
Thanks.
Anyone else? There's a question there, Peter.
Do you understand how to perform gauging of non-invertible symmetries using the ZX calculus?
For G, I know. So we have I didn't give a reference, but it's very closely related to this. So you can.
I mean for rep G?
Yes, you get a dual rep G symmetry, and this is the operator you get. So you start with X on one side, you get Z on the other side, and that's how you go from G to rep G in a non-abelian. Yeah. For a non-group, I'm not sure yet.
Yeah, so I was more interested in the non-group case. Another question is, so for the more general Hopf algebras, like started from the simplest, like the rep of H8, can that also be realized on this using the ZX calculus?
I think it might be possible. I'm not sure people have done it yet. In the quantum information community, people have stuck to either qubits or like Z-valued SU2, but not something, not a general rep yet. So I think it would be interesting to see what we can do together.
Thank you.
Okay, I think we should wrap up there. Let's thank Nat for a very beautiful talk.